Thanks so much, and thanks everyone for having me. So as it says on the slide, I'm going to talk about joint work with my colleague Ben Elias, my former student Dane Miata, and Lorenzo Vecchi, who's now a postdoc in Sweden. So let me just briefly tell you my plan. So in the first half of the talk, I'm going to introduce the notion of a valuation or valuative invariant for polytopes or matroids, and I'll give a few of my favorite examples: a trivial invariant, a Poincare polynomial, and Chow and augmented Chow polynomials, and I'll state some theorems, a theorem and a conjecture about each of these invariants just to kind of motivate them. And then in the second half, I'm going to sort of redo it all in a more categorical framework. Okay, so let me start with a real vector space V. So a polytope in V is just a convex hull of a finite set of points, you know. And I want to think about the free abelian group with basis given by all polytopes in V. So this is some hugely infinite dimensional free abelian group. Okay, and I want to think about a subgroup, the kernel of the homomorphism that takes a polytope to its indicator function. So let's just think about an example. So we've actually seen this example in a talk earlier this week. So we have the octahedron, which I can split into the upper pyramid and the lower pyramid. And the indicator function of the upper pyramid plus the indicator function of the octahedron minus that of the upper pyramid minus that of the lower pyramid plus that of the square on which they intersect is 0. Therefore, this sum, this alternating sum of 4 terms is an element of my group I of V. Here's another example. So the big triangle is minus the 4 small triangles plus the 3 internal edges is 0. So that alternating sum of indicator functions vanishes. Okay. So I've given you 2 examples of elements of I of V, and I claim that they all basically arise this way. So a decomposition of a polytope is a collection of polytopes so that it's closed under taking faces. The face of an element in my collection is again in my collection. 2 polytopes in my collection intersect at a common face, and their union is the big polytope P. So I've just given you 2 examples of this. The first example was a decomposition of the octahedron, and the second example is a decomposition of the big triangle. And elements of the decomposition are called faces, and I'm particularly interested in the internal faces, so faces that are not contained in the boundary. So in this example, we have 4 two-dimensional internal faces, the 4 small triangles, and 3 internal edges. I mean, there are 6 non-internal edges, but 3 internal ones, yeah? What's that? That's right. So actually, I have a lot of faces in here. I have I have a bunch of vertices. I have a lot of edges. It's not closed under internal faces, but it's closed under faces. So some of the faces in my decomposition are internal and some are external. So here, in this particular decomposition, I have 6 vertices. None of them are internal. I have 9 edges. 3 are internal and 6 are external. And I have 4 two-dimensional faces. Right, so the 4 things appearing on the bottom line are the 4 internal faces of my decomposition. My decomposition has a lot more faces that are not internal. The internal faces are not closed under faces. The faces are closed under faces. Any other questions? Okay, so in this case, I have no internal vertices. I have 3 internal edges, and I have 4 internal triangles. And the theorem is that whenever I have a decomposition, I have an element of I of V given by the thing that's being decomposed and the internal faces of my decomposition, some of which appear with a positive sign and some of which appear with a negative sign, depending on the dimension. And in fact, I of V is spanned by elements of this form. So the two examples I gave you, really, I of V is spanned by exactly that kind of thing. Okay, so suppose I have an abelian group and I have a homomorphism from pol V to the abelian group. In other words, I have an element of my abelian group for every polytope. So I think of this as some sort of invariant of polytopes. So this is called a valuation if I of V is contained in the kernel. In other words, whenever I have one of these decompositions, my invariant of P, my phi of P, is equal to an alternating sum of phi of Q, where Q ranges over the internal faces of my decomposition. So that's what it means for a homomorphism to be a valuation. The first example is the trivial homomorphism that takes every polytope to 1. And I claim that this is not obviously a valuation. So I will give you a proof later in this lecture, and it's not super hard, but for those of you who are bored over the next few slides, maybe you can think about, how would you prove that even this trivial homomorphism actually is a valuation? It's not totally obvious to me. Okay, let me now restrict to a particular class of polytopes coming from matroids. So this is something we've seen earlier in the week, but I'll just say it again anyway. So a matroid on the finite set E is a non-empty collection of bases satisfying the basis exchange property. So if you have two bases and an element of 1, you can swap it out for the first. And I want to say the rank of a matroid is the size of any basis, and they're all the same size. And the example to keep in mind, again, we've seen this earlier, but I'll say it again. Suppose I have a bunch of vectors in some vector space that span it. Maybe I have a 15-dimensional vector space, and I have 100 vectors in that 15-dimensional vector space that span the set. A set of 15 of those vectors may or may not be a basis. Some of them are, some of them aren't. And the data of which ones are a matroid, is a matroid. So the collection of subsets such that the corresponding vectors is a basis, that's a matroid, and the rank is equal to the dimension of the vector space. So such a matroid is called realizable over C if it's a complex vector space. So each matroid determines a polytope. Again, we've seen this construction, but I'll just give it again. So we're in RE, where E is the size of the ground set, and it has basis X sub E. And for any set, I write X sub S as sort of the 0, 1 vector that's 1 on that set. And then the polytope associated to the matroid is the convex hull of the XBs, where B ranges over all bases. So I want to define mat E to be the subgroup of this group of with basis given by polytopes, but I want it to be just the subgroup given by matroid polytopes. And I want I of E to be mat E intersect I of RE. A theorem which sort of sounds obvious at first, but is really not at all obvious, is that IE is generated by elements associated with decompositions of matroid polytopes into matroid polytopes. You might think that you have a matroid polytope and you can decompose it into a bunch of pieces that are not matroid polytopes and then reassemble them into a different matroid polytope in another way, and then you have a relation in IE that doesn't come from decompositions into matroid polytopes, but in fact that's unnecessary. So to understand IE, it is sufficient to just think about decomposition of matroid polytopes into other matroid polytopes. So this is actually a pretty deep result. And again, I want to define valuations the same way. So a homomorphism from mat E to A is a valuation if I of E is contained in the kernel. So I want to give some examples where my abelian group is Z of T. So such a homomorphism, it's just a way to associate a polynomial with any matroid. And saying it's valuative is saying that these polynomials are additive over decompositions of matroid polytopes. So the first example I want to give, I'm going to define as follows. So there's a ring, a graded ring associated to a matroid called the Ehrlich-Solomon algebra. It's defined by explicit generators and relations. If you know what it is, great. If not, I will tell you what it is in the special case of a realizable matroid. So if my matroid comes from a bunch of vectors in a complex vector space, let me look at the hyperplanes that are perp to those vectors in the dual vector space. So now I have a finite set of hyperplanes in a complex vector space. I remove them, and I get some interesting topological space, and I take the cohomology of that space. So that's the Orlick-Solomon algebra. It's a graded ring. And I want to define the Poincare polynomial of the matroid to just be the Poincare polynomial of that algebra, so the generating function for the dimensions, graded dimensions of that algebra. So again, in the case of a realizable matroid, this is actually a Poincare polynomial of a space. And if that terminology isn't familiar, you might know about the characteristic polynomial of a matroid. The characteristic polynomial is just the Poincare polynomial backward and with signs. So it's encoding exactly the same information. Just for motivation, this is sort of a side remark. Here's one reason you might be interested in the Poincare polynomial. There's this famous theorem of Adeprecito, Ha, and Katz from 2017, which says that the coefficients form a log concave sequence. So if ai is the coefficient of t to the I, then ai squared is greater than or equal to ai minus 1 times ai plus 1. So a theorem of Speyer from 2008 is that the Poincare polynomial is valuative. So the homomorphism that takes a matroid to its Poincare polynomial is a valuative homomorphism from mat E to z of t. And I'll just point out a couple of things. I'm being a little bit loose with notation, so I'm writing m rather than p of m to denote a basis element of mat E. I hope that's not too confusing. And I'll also mention Speyer proved something a little stronger. He proved that the top polynomial is valuative, and pi m of t is an evaluation of the top polynomial. Therefore, that's also valuative. Okay, I want to talk about two other similar polynomial invariants of matroid. So the first comes from something called the Chow ring. So this is denoted ch underline of m. So like the Orlick-Solomon algebra, it's also defined by explicit generators and relations, and it also has a cohomological interpretation in the case of realizable matroids. So when m is realizable over C and U is the corresponding hyperplane complement, this is the cohomology of some compactification of the projectivization of U. So I take U and I mod out by scalars, and then I compactify that in a nice way. It's called the wonderful compactification, and I take the cohomology of that. So in some sense, if this is going by too fast, it's not a big deal. It's just another example that if it's familiar to some of you, that's great. Otherwise, you're welcome to ignore it. But maybe the main way to think about it is there's some graded vector space, in fact, graded ring associated with the matroid, and it's just the Poincare polynomial of that ring. So sorry, that's the Chow polynomial. It's the Poincare polynomial of the ring. That's right, although they're the same up to a factor of 2, so it doesn't really matter. And there's a closely related ring called the augmented Chow ring, and the augmented Chow polynomial comes from that. Again, if you know it, great. If not, then don't worry about it. It's just another example in the list. Okay, again, just to sort of motivate thinking about these polynomials at all, let me state a fun conjecture relating them. So first of all, these polynomials are both conjectured to be real-rooted with distinct roots. And the roots are conjectured to interlace. So if my matroid has rank 5, then the augmented Chow polynomial has degree 5, so it has 5 roots. And the Chow polynomial has degree 4, so it has 4 roots. And they interlace like this. So that's the conjecture. Totally open. A theorem of Ferroni-Schroeder in one case and Ferroni-Mathern-Stevens-Vecchi is that these two polynomials are both valuative. And let me point out now, I don't particularly think this theorem is going to be helpful in proving the conjecture, but it was extremely helpful in generating the conjecture. Louis Ferroni in particular has spent a lot of time computing these polynomials for thousands and thousands of matroids, and he's strongly using the valuative condition to do those calculations. So yeah, so this valuativity result is super helpful for doing calculations, and in particular motivates this conjecture. Okay, so let me spend some time outlining a proof that the Chow polynomial is valuative. I mean, I won't give the whole proof, but let me give some idea of how it's proved. So let me, yes?
Just a quick question. You have defined two polynomials that look very similar. Can you compute one from the other?
You can compute the augmented Chow polynomial if you know the Chow polynomial of M and all of the contractions of M.
No, sorry, I meant it with the Poincare polynomial and the Chow polynomial.
Oh, no, I think they're pretty unrelated to each other, at least to the extent of my understanding. Yeah. Okay. So let me go back to the world of polytopes. So suppose, remember I have this ambient vector space in which my polytopes live. So suppose I have a linear functional on that vector space. And for every polytope, let P sub psi be the face on which that linear functional is maximized. You know, maybe it's a vertex, maybe an edge, whatever. And let me consider the homomorphism that on the basis, I mean, it takes every polytope to the face on which psi is maximized for that polytope. So a theorem of McMullen from 2009 is that this homomorphism, in a sense, is valuative. The homomorphism takes I of v to I of v. So if I have a relation coming from a decomposition of P, and I apply this to it, then I get, again, some relation coming from decompositions. So let me illustrate this in an example. So let me take the linear functional that measures, up and to the right. So it's a linear functional on R2 that takes A plus B. And let me look at this example that we've done. So the element of IV that we looked at is P minus the 4 small triangles plus the 3 internal edges. And when I apply delta psi to it, P turns into P psi, which is the interval. And the 4 small triangles turn into A, B, G, and F. Right? Most of the small triangles, psi is maximized on an edge, but for the middle one, psi is maximized on F. And then the 3 internal edges turn into some things. So you see I got a bunch of stuff and some cancellation. And after the cancellation, it becomes P psi minus A minus B plus F. And that is also an element of I of V coming from a decomposition of P psi.
Is it the case more generally that if you take any linear section, you replace a polytope by just a linear section?
Yeah, but this is different from that. Yeah. So I think that'll be true also, but this is somehow more subtle. So this is the element of I of V corresponding to the induced decomposition of P psi, where there are 3 internal faces, A, B, and F. Okay, so now let me specialize to the matroidal setting. Suppose my ground set decomposes as a disjoint union. E breaks up into E1 and E2. So if I have a matroid M1 on E1 and M2 on E2, I can build a matroid on E. Often this is called the direct sum. I'm going to call it the disjoint union because I'm going to be using direct sum for something else, and I don't want to get too confusing. So this is a matroid on E whose bases are unions of a basis for M1 and a basis for M2. And the polytope for the disjoint union M1, disjoint union M2 is just the product of the polytopes for M1 and M2. So for example, if M1 is given by a bunch of vectors in the vector space V1 and M2 is given by a bunch of vectors in the vector space V2, then the disjoint union is just given by the disjoint union of the vectors where I put a 0 in the other coordinate. So let me look inside of mat E and just look at this group called mat E1, E2, which is just the subgroup spanned by matroids of this form. So most matroids don't break up as disjoint unions, but some of them do, and let me look at that subgroup. So mat E1, E2 is just mat E1 tensor mat E2. and I of E intersected with mat E1, E2. In other words, decompositions of matroids of this form basically come from decompositions of matroids on E1 times whatever matroid on E2, plus decompositions of matroids on E2 crossed with whatever matroid on E1. Conversely, given a matroid on E, we can construct a new matroid on E1 by deleting E2, and a new matroid on E2 by contracting E1. We can sort of break it into a matroid that comes from E1 and E2 separately. So for example, if I have a collection of vectors in V, to get my matroid on E1, I just take the vectors in E1, and which are already, I take V1 to be the span of the vectors in E1, and then that gives me my M1. And I take V2 to be the quotient by V1, and I project things onto V2, and that gives me my matroid M2. So a basis for this thing is just a basis of M with the property that when I intersect with E1, I get a basis of M1, or equivalently, when I intersect with E2, I get a basis for M2. In particular, this broken matroid, M1 disjoint union M2, the set of bases is a subset of the set of bases for M, so I have an inclusion of polytopes. So let me define a linear functional that just takes the sum of the E1 coordinates, right? I have a whole bunch of coordinates for E, which is E1 union E2, and I just take the sum of the E1 coordinates. So then when I do this trick of taking the face on which the linear functional is maximized, I end up getting exactly this subpolytope corresponding to the broken matroid. So the P of M1 disjoint union M2 turns out to be a face of P of M, and it's the face on which this linear functional is maximized. So we can think of delta sub psi as a homomorphism from mat E to mat E1 tensor mat E2, and it takes M to M1 tensor M2. So putting everything together, we get the following construction. So suppose I have I have an invariant of matroids on E1 that takes values in a polynomial, and I have invariant of matroids of E2 that takes values in a polynomial, and they're both valuative. They're both valuations. I'm going to define an invariant of matroids on E. So what do? I take my matroid on E, I break it into a matroid on E1 and a matroid on E2. I apply my first valuation to the matroid on E1, my second valuation to the matroid on E2, and I multiply them together. Right, so that's exactly what I just said. So a theorem of Ardila and Sanchez from 2 years ago is that this new homomorphism is also a valuation. Okay. So here's the procedure again. So phi1 star phi2 is also a valuation. So let me sort of explain how we can get from here to valuativity of the Chow polynomial. Well, let me quickly give a proof of this theorem. So by McMullen's theorem, this delta psi takes I of E to I of E1 tensor mat E2 plus mat E1 tensor I of E2. And since phi1 kills I of E1 and phi2 kills I of E2, when I multiply them together, I kill I of E. Right. So Ardila and Sanchez's theorem is basically a corollary of McMullen's theorem in the world of polytopes. So let's tie this back to the theorem about the Chow polynomial. So an element is a loop if it's not contained in any basis. And I say that E1 is a flat if when I contract it, there are no loops. Right, so if M2 has no loops. So for a given subset of E and a given integer, positive integer, I want to consider the homomorphism from matroids on that subset to Z that takes a matroid to 1 if M has no loops and is of rank K and 0 otherwise. And it's pretty trivial to show that this is a valuation. And suppose I decompose E into a whole bunch of subsets, and I convolve the corresponding these corresponding valuations. So by Ardila and Sanchez, my new thing is a valuation. And this new thing that I've made gives me 1 if this union of subsets gives me a chain of flats of prescribed rank. So S1 should be a flat of rank K1, and S1 union S2 should be a flat of rank K1 plus K2, and S1 union S2 union S3 should be a flat of rank K1 plus K2 plus K3, et cetera. So using this Ardila-Sanchez theorem, I can now detect whether a certain chain of subsets is a chain of flats of a prescribed rank. And there's a really nice basis for this Chow ring given by Feichner and Uzvinsky, which is indexed by chains of flats along with some auxiliary data. And basically, trying not to be too technical, if there's a valuative invariant that can detect and therefore count chains of flats, and if my algebra has a basis given by chains of flats, then valuative invariants can detect the Poincare polynomial of my algebra. So that's the corollary that says that the homomorphism taking M to its Chow polynomial, well, it's equal to a Z of T linear combination of these homomorphisms, and therefore it's valuative. And a similar argument can be made for the augmented Chow polynomial. Okay, so just to quickly recap, I have these polynomials, the Poincare polynomial, the Chow polynomial, the augmented Chow polynomial. They're all valuative. That makes it really easy to compute, which is great. But the valuativity condition itself is kind of mysterious and the proofs are opaque. So I want to understand better what's really going on with valuativity. What's behind these theorems? Why are these things valuative? So let me go back to trying to understand the trivial homomorphism, which, as I claimed, is a little more subtle than it sounds. I claim that this is not completely obviously valuative. So let me explain to you at least the way that satisfies me, why is this a valuation? So suppose I have a decomposition of a polytope called Q, and let me choose an orientation of all the faces in my decomposition. So the faces are the cells in a cell complex with total space P. And we have the corresponding cellular chain complex, where we have all the cells of dimension P, all the cells of dimension P-1, et cetera. Right now, I'm talking about all the cells, not just the internal ones, including the ones on the boundary. But if we kill the terms corresponding to the boundary faces, we're left with only the internal cells. Now we have a cellular chain complex, not for the cell complex P, but for the pair P relative to the boundary of P. So now we just have the internal faces. The homology of this complex is equal to the homology of the pair, which is one-dimensional and concentrated in top degree, right? Because it's a disk relative to its boundary. We can build an exact complex by adding one more copy of Q in the beginning, right? And now we know that the Euler characteristic is 0, right? So 0 is 1 minus this alternating sum of a bunch of copies of 1. But that's just the trivial invariant applied to the corresponding element of I of V, right? Tau of P minus the alternating sum of tau of Q's for Q ranging over the internal faces. So that topological argument, that Euler characteristic argument, at least to me, explains why the trivial valuation is a valuation, why the trivial invariant is a valuation. So this is precisely the statement that tau vanishes on the generator of I of V corresponding to Q. So, okay, this sort of suggests that these alternating sums should be replaced by exact sequences in the notion of valuativity. So let me try to do that. So suppose instead of an abelian group, P of V, I want a category, curly Q of V, curly P of V. So the objects are polytopes in V, or formal direct sums of polytopes in V. And the hom from P to P prime is just a copy of Q if P prime is contained in P and 0 otherwise. So given a decomposition of a polytope P with choices of orientations, I can build a complex exactly as before. So P maps to all the top dimensional faces, maps to all the top -1 dimensional faces, to top -2 dimensional faces, And all of those maps are given by sort of plus or minus the generator of the Hom set, depending on the orientations.
So that inclusion, is it just as sets, or does the faces need to match?
Let's just say as sets, although here, I mean, there's sort of two types of inclusion. One corresponding to the first map, where all of those top dimensional faces of P are actually the same dimension as P, and the others are all face inclusions. In fact, they're all facet inclusions because we're going down by one each time. Okay, so now let me categorify the notion of an invariant or a valuative invariant. So instead of taking values in an abelian group, it'll now take values in an abelian category. So I want a functor from this category of polytopes to an abelian category, and it should be a categorical valuation if it takes this complex to an exact sequence. Right? And when you pass to Grothendieck groups, maybe I wrote that, if you take A to be the Grothendieck group of curly A, then if I have a categorical valuation, then I have an induced map on Grothendieck groups from Pol V to A, and that's an ordinary valuation. So this categorical notion exactly categorifies the notion of a valuative homomorphism. So for example, so this is the categorization of the trivial invariant. I have the trivial functor that takes every polytope to the one-dimensional vector space Q and every inclusion of polytopes to the identity map. And the argument I gave was just that this is a categorical valuation, and it categorifies the valuation tau. In fact, I proved that the non-categorical homomorphism tau is a valuation by categorifying it and proving that that categorical version of the trivial functor is a valuation. So let me do the same thing on matroids. So we have a category of matroids where the objects are given by matroids themselves, or formal direct sums of matroids, and the morphisms are given by inclusions of matroid polytopes. These are often called weak maps of matroids. And then a categorical invariant of matroids, in other words, a functor from the category of matroids to some abelian category, it's a categorical valuation if it takes the corresponding, for any decomposition of a matroid polytope into matroid polytopes, it should take the corresponding complex to an exact sequence. So an example, I mean, I won't give the full example, but whenever I have a weak map of matroids from M to M prime, in other words, whenever the matroid polytope of M prime is contained in the matroid polytope of M, there is a completely canonical ring homomorphism from the Ehrlich-Solomon algebra of M to that of M prime. In fact, the Ehrlich-Solomon algebra of M prime is a quotient of the Ehrlich-Solomon algebra of M. I didn't give you the presentation, so this doesn't follow from what I told you, but it follows immediately from the presentation if you write it down. So I have a functor from M of V to the category of graded vector spaces. It categorifies the Poincare polynomial. And, well, first of all, this functor is evaluation. So this is Ben Elias, Dane Miata, myself, and Lorenzo Vecchi. And you can do something similarly for the Chow ring and the augmented Chow ring. So I can define a functor from the category of matroids to the category of graded vector spaces that takes every matroid to its Chow ring, or takes every matroid to its augmented Chow ring. Not just any functor. I mean, I could do that really stupidly where all the maps go to 0. But in fact, there's a smart way to define these functors in such a way that the categorical invariants are valuative in the categorical sense. The proof of the first statement has a similar flavor to the proof that the trivial functor is a categorical valuation. And the second statement, well, I won't give you the full proof, but just like in the non-categorical setting, the key to the proof that the Chow polynomial was valuative was McMullen's theorem. So in the categorical setting, the key to the proof is a categorical analog of McMullen's theorem, which I'll now explain. So suppose I have a real vector space and I have a linear functional on that vector space. Again, for any polytope, I let p psi be the face on which psi is maximized. And now let me define the corresponding functor. So it takes p to p psi. If p prime is contained in p and p prime psi is contained in p psi, then I just take the map, the associated map from morphism from p to p prime to the associated morphism from p psi to p prime psi. and otherwise I just send it to 0. So it may be that P prime is contained in P, but the face on which P is maximized is up here, and the face on which the face of P on which psi is maximized is up here, and the face of P prime on which psi of x maximized is down here. And then this doesn't include in here, so then the map has to go to 0. There's nowhere else for it to go. Okay, so the theorem, which is the analog of McMullen's theorem, is that if I have a decomposition of P, and then I have an induced decomposition of P psi, then when I apply this functor to the complex associated with the decomposition of P, I essentially get the complex associated to the decomposition of P psi. I don't quite get it. I only get it up to homotopy of complexes and up to a shift, but I get it nonetheless. So let me go back to the example we've done before. So if the complex associated with Q, I have P going to the direct sum of the 4 small triangles going to the direct sum of the 3 internal edges. So what happens when I apply this psi functor to that? So So P turns into P psi. The small triangles turn into G, A, F, and B. But you see, G doesn't include into P psi. So P psi doesn't map to G in the complex. It only maps to A, F, and B. And the internal edges, 2 of them turn into F, and 1 of them turns into G. But, I mean, here's how the maps work. This thing from G to G, that sort of sits by itself, and it's null homotopic. So up to homotopy, that part just goes away. And the rest, well, you can sort of massage this complex. Up to homotopy, you can get rid of 2 of these copies of F. So up to homotopy, I get P psi going to A and B, which then go to F. And that is the complex associated with the decomposition of P psi. So this is isomorphic to the complex associated with P psi, but shifted 1 degree to the left. Okay. There are in fact 3 Fs because I have 3 internal faces, all of which, 3 internal faces, all of which go to F. So I have this edge, which goes to F when I maximize psi. I have this vertical edge, which goes to F when I maximize psi. And I have this middle triangle, which goes to F when I maximize psi. So those are my 3 copies of F. And up to homotopy, 2 of those can be collapsed, and 1 of them is left. Question? Okay, so this is the categorical notion of evaluation. And I mean, one reason I like this is I feel like it explains why these things are valuations. Like it gives a more satisfying explanation. But there's also something you can do with categorical valuations that you can't do with ordinary ones. So some categorical valuations of matroids, like the Ehrlich-Solomon algebra, the Chow ring and the augmented Chow ring, they're functorial not only with respect to inclusions of polytopes, but also with respect to permutations of the ground set. So if I have a finite group that acts on my ground set by permutations and acts on a decomposition of a polytope into other matroid polytopes, then this exact sequence that comes from when I apply the Ehrlich-Solomon algebra gives some relation involving the Ehrlich-Solomon algebra and the Ehrlich-Solomon algebra of the various other matroids appearing in the decomposition, all regarded as representations of my automorphism group. And the same goes for the Chow ring and the augmented Chow ring and many other categorical valuations. So this valuative condition, this categorical valuative condition, is going to allow me to do equivariant calculations that I wasn't able to do before. So let me sort of motivate that a little bit by stating some conjectures about the Ehrlich-Solomon algebra and the Chow ring and the augmented Chow ring, not just as graded vector spaces, so not just statements about the polynomials, but as representations of the group of symmetries of M. And the point is, using the non-categorical valuative condition, you can compute these things as vector spaces. You can compute the polynomials. But given the valuative property, you can actually often compute them as representations of the automorphism group. So the first conjecture is due to myself and my former student Katie Gedian and my colleague Ben Young from 2017. So this is a categorification of the Adorpacito-Hahn-Katz log concavity theorem. It says that the Ehrlich-Solomon algebra is equivariantly log concave. So in other words, not only is the dimension of OS of I squared greater than the dimension of OS of I minus 1 10 times the dimension of OS I plus 1, but it's actually true as representations. So I can take OSI tensor OSI, and that's supposed to be bigger than OSI minus 1 tensor OSI plus 1 as representations of the symmetry group of the matroid. So this is a much richer conjecture. So, the Adorpacito-Hahn-Katz theorem, that's a theorem for all matroids, whether realizable or not. This isn't even known, for example, for the braid matroid. So do I have that here? I don't have it here, so let me just state it. So if M is the matroid associated with the Coxeter arrangement in type A, then OS of M is the cohomology of the configuration space of endpoints in the plane. And even in that case, this is not known. So if you take HI of the configuration space of endpoints in the plane, so HI tensor HI is supposed to be bigger than HI minus 1 tensor HI plus 1 as representations of SN. So this is checked up to n equals 44, and it's proved for all n when I is less than or equal to 7. So I'm quite confident that it's true, but it's still unknown.
Is there any natural morphism from one side to the other?
I don't believe so. Yeah. Let me state, so this is a sort of an equivariant conjecture about the Ehrlich-Solomon algebra. Again, I'm not claiming this can be proved with the valuativity condition, but it can certainly be checked for lots of examples using valuativity. Let me also state an equivariant conjecture about the Chow ring and augmented Chow ring. So let me first remind you of the conjecture I stated before non-equivariantly. So this Chow polynomial and augmented Chow polynomial are supposed to have strictly interlacing real roots. So let me reinterpret this conjecture as a positivity statement. Suppose I have two polynomials whose degrees differ by 1. So f has one bigger degree than g. So I can define the Bézout matrix. It's a symmetric matrix. I take f of x g of y minus f of y g of x, and I divide by x minus y. I get a symmetric polynomial in x and y, and I take the matrix of coefficients. So that's called the Bézout matrix. And there's a theorem that says this condition of having strictly interlacing real roots is equivalent to the Bézout matrix being positive definite. In other words, I check all the principal minors, and I should get positive numbers. And this is nice because this is something that can be interpreted equivariantly. So suppose I have two graded representations. I think of those as polynomials where the coefficients are now not numbers, but representations of my group. So like instead of the Chow polynomial, I have the Chow ring, and I think of that as a polynomial where the coefficient of t to the I is the ith graded piece of the Chow ring, regarded as a representation of my automorphism group. I can define the Bézout matrix in the same way. Product becomes tensor product of representations. Now I'm going to get a symmetric matrix whose entries are virtual representations, because I have some minus signs. And I'm going to say that my two equivariant polynomials strictly interlace if all of the principal minors of the Bézout matrix are honest representations. I mean, a priori, they're virtual representations. They're sort of differences of isomorphism classes of representations, but I want them to be isomorphism classes of honest representations. So this categorifies the notion of being of strictly interlacing real roots. So conjecture of George Nazer and myself is that the Chow ring, thought of as a graded representation of the automorphism group, strictly interlaces the augmented Chow ring. So just to put one example on the board, suppose I take the Boolean matroid on 1, 2, 3. So 1, 2, 3 is the unique basis. If I take the Bézout matrix of the Chow ring and the augmented Chow ring, I get a bunch of virtual representations of S3. It turns out that the entries end up being honest representations, not virtual representations. That wasn't obvious from what I told you. And you can look at the principal minors of this matrix, and they're all non-zero honest representations. In fact, something really weird happens. Not just the principal minors, but all minors of this matrix are non-zero honest representations. So this matrix is more than equivariantly positive definite. It is in fact equivariantly totally positive. And that happens in all of the examples that we've checked for more complicated matroids. I don't know what that means in terms of the polynomials. You know, positive definite Bézier matrix means that the polynomials have interlacing real roots. Totally positive Bézier matrix, I just have no idea what to make of that, but it seems to be true in all examples. And that's where I'll stop. Thank you.
Thank you, Nick, for a wonderful talk. Are there any questions from the audience? Oh, wow, great.
Do you conjecture that for the first one, the Orlick-Solomon, does that hold for all matroids?
All matroids, yeah,
Thank you.
conjecturally.
Thanks for the really cool talk.
Thanks.
I'm curious about the sort of behavior of these decompositions. Is there a sense in which you can sort of do like a homotopy of the big polytope onto the internal pieces? Like, is there a collapse going on? Is there a...
Nothing that I know how to make sense of.
Okay.
I really think of it as a cell structure on the polytope. I mean, the polytope itself is a ball, but you can have a cell complex, you know, dividing that ball into smaller balls with lots of cells, and that's where these complexes come from.
Okay. Yeah, I was just sort of thinking, because you're sort of taking a subset of the face poset and kind of just restricting your attention to that. I was wondering if there's a...
Yeah, nothing that I know how to make sense of.
Thanks.
I can just talk about it. So for this last conjecture about the Bézier matrix and positivity, do you know if there's any connection to the Schur positivity conjecture of like Lamb, Piliofsky, Postnikov on, you know, products of two Schurs minus products of two Schurs?
Yeah, so the question, if people are on Zoom, was whether this conjecture has anything to do with the Schur positivity conjecture, and no, I have no idea. Sorry.
Okay. And I have another really quick question. Have you considered extending any of this to polymatroids and like generalized permutahedra?
Yes, I mean, I suspect that theory would go through fine. So the Dirksen-Fink theorem applies not only to matroids but to polymatroids. So I mean, you can work at, you know, I talked about matroids and I talked about polytopes, but you can go higher. You can talk about all polyhedra, not just polytopes. You can go down to polytopes. We haven't done it, but I suspect you could do polymatroids, which sits in between polytopes and matroids. So I suspect that this notion of categorical valuativity works at a lot of different levels up the hierarchy. So we focused on the level at which, you know, most of the examples we cared about lived. But
there'd be an alternative categorification of real rootedness by looking at the tuplets matrix associated to the Chow ring. Do you know if the equivariant positive semi-definiteness of this matrix would imply the equivariant total positivity of that matrix?
yeah, it's a good question. Something I've thought about a little and have been meaning to think about systematically, but have not done yet. Yeah, there are so many equivalent notions of, equivalent ways to formulate real rootedness in the non-equivariant setting, in terms of the Bézier matrix, in terms of the Toeplitz matrix, in terms of factoring, you know, various things, and you can sort of equivariantize any of those definitions, and I believe that they are not equivalent after you make them equivariant, but you can still ask which ones imply which other ones, and try to go through this systematically. The Toeplitz matrix is an infinite matrix, and there are infinitely many things to check, even to see that a quadratic thing is real rooted. So I kind of don't like that as much, and when I have things that supposedly interlace, I like this a lot better. But I do think that it would be interesting to really systematically develop the theory of equivariant real rootedness and all the different various versions of of it and how they relate to each other. Yeah, sure.
I was wondering, maybe I missed it. What do you know about the actual entries?
Right. So the question is, what do we know about the entries of this matrix? Yeah, I mean, the answer is nothing. A priori, the entries of the matrix will be virtual representations. And what we are seeing is that the entries of the matrix are honest representations, and in fact, all minors of the matrix, including the entries themselves, seem to be honest representations. I don't know how to prove that, and I also don't know what to make of that fact, right? Like what I expect is that the principal minors will be honest representations. In particular, the diagonal entries will be honest representations, because this sort of categorifies a statement about real rootedness that has already been observed in a million examples. But there's obviously something even stronger going on here, and I don't know what to make of it. Oh. Maybe Stephen has been waiting, so.
Oh, thanks. I'm similar to Robbie's question. So, I mean, another condition for positive definiteness is you can factorize your matrix as, say, like B transpose. Do you know if that happens here? Is that equivalent in the equivariant case?
Yeah, I've thought about that a little. It doesn't factorize nicely over the integers. See, equivariantly, it feels really weird to start using rational numbers because you're doing fractions of representations. So there may be something interesting to say there, but I've never found it.
Is the Orlik-Torau valuative, and on the other side, what's the categorification of the Tut polynomial?
Right. So I don't know how to categorify the Tut polynomial, although maybe there's something to be done there. Orlik-Torau is not something that is assigned to a matroid. It's something that's assigned to a hyperplane arrangement. So the Orlik-Torau algebra, and in fact the reduced Orlik-Torau algebra, are conjecturally equivariantly log concave. So that's great, but I don't have a valuativity statement. The Orlik-Torau algebra of a hyperplane arrangement is closely related to the Cordoville algebra of an oriented matroid. I haven't thought about valuativity in the context of oriented matroids, but maybe with what I've been learning from Chris this week, that might be a possible way to go, and that would be related to that statement.
I want to ask clarification because before you had a conjecture in which you had categorification of log concavity, and you had conjecture and inclusion between two representations. But then someone asked if you think there is a natural morphism from one to the other, and you said you don't think so. Is it why aren't you conjecturing even more than a natural morphism?
Yeah, I mean, right. So I have various reasons to not think that there's a canonical inclusion. I mean, of course, I do think that there's an equivariant inclusion. That's the construction. That's the conjecture. The question is there a canonical equivariant inclusion? And what could canonical mean? So these things are FI modules. So not only is there a map from the configuration space of endpoints in the plane to itself when I permute the points, but if I have an injection from a set of size M to a set of size N, then I have a map, given a forgetful map from the configuration space for N to that of M, and then I dualize on cohomology, I get maps the other way. So you can ask, are there inclusions or maybe surjections going the other way that are consistent with the FI module structure? I'm pretty sure that the answer is no. Again, I don't have a proof that there isn't, but I'm pretty confident that there aren't natural inclusions. But yeah, that's not a precise statement.
If there aren't any other burning questions, we can thank Nick again, and our next talk will start at 10.